to speak about stellar nucleosynthesis. Just to recap, what I discussed is the fact that in the Big Bang nucleosynthesis, you have very little, only light element. The second point is that stars need to lose energy. It needs, and this necessity implies that it is transforming, it is evolving, and one way of compensating for the loss of energy is through nuclear reaction, which allows stars to live longer. And this nuclear reaction produces heavier elements from lighter one. So it produces new elements, you see. This is the story. So now I will go into something which is more quantitative, and actually there is a field in astrophysics which is called nucleosynthesis, which are the origin of the elements. Actually, what we would like to do is to trace back a kind of genealogic tree for each element. And what does it mean for an element? It means to find the nuclear processes which are responsible for its synthesis. You need to know the reactions. Then, once you have the reaction, you need to know what are the conditions that are necessary for them to occur. What are the conditions in terms of temperature, density, but also chemical composition. If you need to make helium, you need hydrogen. And finally, once you have answered these two questions, you can think in which kind of objects in the universe I can find this condition realized. And you can find them at the beginning of the universe, you can find them at the center of the star, and you can find them also in the interstellar medium by their interaction with the galactic cosmic rays. This is what I call the spallation nucleosynthesis, on which I will not say much except that they produce light elements like lithium, beryllium, and boron. By the way, just a parenthesis here, lithium is the most complicated element in the universe. Actually, you have astrophysicists who have worked their whole career on lithium. Why? Because lithium can be produced during the Big Bang nucleosynthesis. It can be produced by spallation reaction, by this interaction between cosmic rays and interstellar medium. It can be produced and destroyed in stars. So lithium is eating at every table, you see. And it makes this element one of the most complicated ones. But I will not speak about lithium. So once you have answered the question about the site of the nucleosynthesis, you will have to do models to see whether it fits, whether if you put in these models all the conditions, whether you obtain the quantity of elements which are required to reproduce what we observe. Of course, stars, as I said, is an important melting pot, but it is only one part of the story. Once the elements has been produced in stars, they have to be injected outside, because if they remain locked into a white dwarf, locked into a neutron star, or locked into the black hole, nothing will happen to these elements. Actually, the oxygen that we are breathing now, that are in our body, was at a given point inside the star, but also at a given point ejected by the stars. And then it has to be mixed with the interstellar medium, and this interstellar medium has to form new stars and planets and habitants. So it's a very complex history, this story of nucleosynthesis. I have here Mendeleev tables where you will see that each element is actually has different colors. Sometimes one color, sometimes two, sometimes three, and because the colors are linked to the sources of that element, one of the main sources. If we look, for instance, at hydrogen, there is only one color because it comes from the Big Bang. Actually, it means that hydrogen is the oldest element. Every hydrogen has 30.8 billion years. Now, if you look at some other element, like carbon, for instance, it comes from low mass stars and also a little bit from exploding massive stars. So you have some elements which have different sources. The most recent one of these sources was the merging neutron stars. You may have heard that the last event which was detected by gravitational waves was the merging of two neutron stars. Actually, LIGO, Virgo have detected first merging of black hole. this merging black hole produce gravitational waves. It means waves of the space-time medium, but did not produce any electromagnetic light, any light. While the merging of neutron stars has produced also light. And from this light, and especially from its variation with time, it has been concluded that during this process, some heavy element produced by neutron catcher have been produced. So neutron stars are also, I would say now, a source of elements, merging of neutron stars. Okay, it's complicated to treat the question of nucleosynthesis, especially of stellar nucleosynthesis, because either you list a whole series of processes of nuclear reaction rates and so on, and it becomes like a list, not so much interesting, or you focus on one element and you tell its story. I have chosen this second part. Of course, it's just one element at the end, but still it gives you a flavor on how we do research in this domain, and maybe this is the main point. And I've chosen to speak about oxygen. Where does the oxygen come from? And there is a whole book that was edited by Grazina a few years ago, which is entitled Oxygen in the Universe, to which many people have participated, and I wrote one of the chapters about stellar nucleosynthesis of oxygen. That's why I use this material here. And take it as an example. Actually, oxygen is a good case because we know more or less well the answer. Where does it come from? It comes mainly from massive stars. And massive stars have, there are very, I would say, efficient nuclear reactors. Just a point here, you know that the lifetime of a star, we have seen this in the previous lecture, depends on the quantity of fuel that we have, on the mass, but is inversely proportional to the luminosity. But as we saw, the luminosity depends on the mass to the cube. So you have the lifetime of a star depend on the mass divided by the mass to the cube. So it means that when you increase the mass, you decrease the lifetime. And so, for instance, 100 solar mass stars have a lifetime during the main sequence of about 3-4 million years, while the Sun has a lifetime of 10 billion years. So you have a factor of 100, of no more, between 10,000 between the lifetime of the Sun and the 100 solar mass stars. So in order to make oxygen, you need first to look or to find the nuclear reactions which are needed to produce oxygen. And if you begin with hydrogen, you will first produce helium. And in massive stars, helium is produced by a cycle which is called the carbon-nitrogen-oxygen cycle, CNO cycle. Actually, I will not describe in details this cycle. The only point I would say is the following one. This cycle, CNO cycle, actually does not change the total of the abundance of carbon, nitrogen, and oxygen. Typically, if you start with a star which has, let us say, a mass fraction of CNO element of 0.01, 1% of the mass of the star is made of CNO elements. At the end of the hydrogen burning phase, you have still CNO element is 1%. So actually, CNO cycle does not change the sum of the CNO. Actually, the carbon, nitrogen, and oxygen act as catalyst. Unfortunately, the resolution is not so good here, but you have proton capture with the carbon, then you have other type of nuclear reaction. But if you look at what happens, you have 4 protons which at the end are merged into 1 helium by capture by carbon, nitrogen, and oxygen. The point is that in this cycle there is one reaction which is much slower than the others, which is the destruction of nitrogen. At a given point you have nitrogen 14, proton, gamma, and it becomes oxygen 15, I guess. Nitrogen 14, yes, oxygen 15. And this reaction is very slow. So in these processes, you have much of the carbon which will be destroyed to make which will accumulate into the nitrogen. So the CNO cycle does not change the mass fraction of the whole element, but change the distribution of the carbon, nitrogen, and oxygen between them. Typically, nitrogen over C will increase. Nitrogen over O will increase. And what is fantastic is that we can observe that. Of course, I cannot observe what happens at the center of a star. It's not possible. But I can observe if some elements produced at the center of a star arrive to the surface, because sometimes the stars lose mass, they lose their surface, their hydrogen-rich surface, and we can see some layers whose composition has been changed in the past by nuclear reaction. There are no long nuclear reactions in this shell now because they are at the surface at too low temperature. But they were, at a given time, deep inside the star and were uncovered by mass loss. And we can check that it works, and it works. So at the end of hydrogen burning, you have actually a lot of helium and a little bit of nitrogen, which is produced by this transformation of carbon and oxygen. Now, you have no oxygen. Actually, the life of oxygen begins in a bad way. The oxygen that was there actually is destroyed during the hydrogen burning phase, you see. It is destroyed. Of course, if you start with a star which is made of primordial material, where oxygen was not occurring, it's a bit different. Actually, what happens, I tell you in a few minutes, it is that you have only production of helium by fusion of proton, of hydrogen. But this fusion of proton is not energetic enough to sustain the star against gravity. So the star will contract up to the point where the temperature will become high enough for helium burning to occur, because helium has been produced by a Big Bang, so it's already there. And this helium burning will produce a little bit of carbon and oxygen, which will then allow the CNO cycle to occur. Okay, now at the end of hydrogen burning, actually, you destroy oxygen. What will happen after? After, you will have helium, which will be the lightest elements and the one which have the least Coulombian barrier, which have the least numbers of charge which can repulse. And so it will be the first to enter into interaction, who can merge. But here there is a problem. It is a problem that if you take two helium nuclei, you produce actually beryllium-8. And we have seen that the beryllium-8 has a very small lifetime, 10⁻17 seconds. And actually, it was Fred Hoyle who actually used, I think he's the only one who used what we call the Anthropic Principle for doing science. I mean by Anthropic Principle, the principle where anthropic can be with the letter ANTHROPIQUE, in the sense that it started from the fact that we are here, or it started from the fact that there is a lot of carbon in the universe, sufficiently in order to make life, for instance. And he said, if we observe this carbon, we must go beyond the bottleneck. And to go beyond the bottleneck, you need to make this reaction, beryllium-8 plus helium, sufficiently efficient enough, in a rapid way, before beryllium-8 decay. Here, it touched a point of nuclear physics. Actually, for this to occur, for this reaction to be very efficient in making carbon-12, you need some special structure of the carbon-12 atom. Actually, what Fred Hoyle did, he computed an excited state of the carbon atom in order for this reaction to be a nuclear resonant reaction. Resonant, it means it's particularly favored, because it means that the two interacting particles, the helium and the beryllium-8, will have together an energy which corresponds to an excited state of the carbon-12. So it means that the pieces of the pulses will perfectly match, and this makes this reaction very, very well favored. And he computed this excited state. It's not just an hypothesis, he computed the numbers. And when he went to Willy Fowler laboratory in the States, he asked him to measure this state. And actually, Willy Fowler could confirm that this state exists at the energy level predicted by Fred Hoyle. So I think it's a fantastic history, and it shows that it started from a global observation of the universe. You see, the whole universe, the content of carbon in the universe, and deduced the energy level of an excited state in the carbon nucleus. It's incredible. And this is a way of using actually a cosmological observation to infer something about fundamental physics. Actually, we have carbon-12, but still not oxygen. But what happens during the helium burning is that carbon-12 can react with helium, and this made oxygen-16. Fortunately, there is no resonance here, because if there were some resonance, there would be no carbon, because all the carbon would be destroyed to make oxygen-16. So we can see that here we are in face of this kind of fine-tuning, that some people would say fine-tuning of the universe, where you need a good resonance at a good place to make enough carbon, and not at another place to destroy it completely. Anyway, oxygen is produced by triple alpha reaction first, and then by alpha capture on carbon-12 nuclei. And this is a place where oxygen is formed in the universe. I show you now some diagram that we can compute, for instance, when we are doing stellar evolution like me. And you have here a kind of, I would say, radiography of the interior of a star in terms of chemical composition. You have here the mass inside the star. So you start from the center, 0, and when you go out here, you are at 15 times the solar masses, 20 times, 25. 25 was the initial mass of the star. It is a 25 solar mass stars. It is a little less here because it has lost some mass by what we call stellar winds. On the vertical axis, you have abundances in mass fraction of various elements. And you can see here a few of them. You have helium, hydrogen, nitrogen. It's a bit complicated. Actually, what is shown is the abundances of oxygen in the envelope of the star, in the outer part here, and the oxygen abundances at the central part of the star, at the end of hydrogen burning. And you can see that at the end of the hydrogen burning, you have a lot of helium in the core, so it's why helium is at the top here, because all the hydrogen is being transformed to helium. And you have a decrease of oxygen with respect to the value at the surface. The value at the surface is the same as the star had at the beginning, because at the surface there is no nuclear reactions, and in that models we didn't account for any possibility for some diffusion between the central part and the exterior. This diffusion can occur if the star is rotating fast, but here we didn't account for that. So the oxygen here is the initial one. So initially we started from oxygen, which is around 10 minus, a little bit about 10 minus 3, and we decrease it by nearly an order of magnitude, a little less, I would say, due to the CNO cycle. Now the second is exactly the same, but at the end of helium burning. And you can see that oxygen, poof, it is becoming the most abundant nuclei at the end of the helium burning phase in the core of the star. It's not in all the star, because at the surface it has decreased a bit. You see, oxygen has decreased a little bit because actually there was some turbulent atmosphere which actually extended over a large part of the mass of the star, and which took some part of the oxygen destroyed to the surface. And by the mixing, it lowered a little bit the oxygen abundance at the surface. But in the center, it's a huge amount. Actually, of course, here you have produced oxygen in the star. Now, what happens is that there is a further history. It's not the end of the evolution of the star. Actually, the carbon will burn, the neon will burn, and after oxygen will burn, and after oxygen burning in the central part, there will be silicon burning. And the silicon burning will produce an iron core, and this will be the end of the story, because after iron, you cannot produce energy by charge particle reactions. So part of this mass which is here will be burnt, oxygen will be burned in part of the central part. But still, in some part of the star, oxygen will remain at this high level. And when the star explodes as a supernovae, this matter can be expelled in the interstellar medium. And this is how oxygen is produced in the universe, by stars more massive than about, let's say, 10 solar masses, 10 solar masses, and below about, by the massive stars, and those which are not producing black hole, for which all the matter is swallowed, because otherwise, in that case, nothing go out from the star. So for between stars, between 8, 10, and 25 solar masses. Here I have indicated in this small, I would say, table, the lifetime of the different phases of nuclear burning. So hydrogen, helium, for massive stars, hydrogen, helium, carbon, neon, oxygen, silicon. And you can see we start with hydrogen 6.6 million years. It's for 25 solar mass stars. The helium is about, you have to make the difference because it is the age, it's not the duration. So you have to make 7.3 minus 6.6. So it's about 0.7, it's about 10%, you see. But if you go toward a very advanced phase, it's even incredibly fast, you see. Silicon burning, it's less than the 10th of a year. What is funny, this is just a small remark, is that when you are doing stellar models, when you are computing a main sequence, you are computing a main sequence in a few hours, maybe 2 hours, 1 hour. It's very rapid, you see. When you want to compute this phase, it can take more than 1 month. So you have a kind of reversal, you see. The reality becomes shorter than the simulation when you go to one advanced phase. And it probably means something. Okay, but I don't know exactly what. Why is the hydrogen burning phase the longest? Because it is a phase during which the star has the smallest luminosity. In general, the luminosity increases with the age. So it is a phase during which the escaping energy is less. Second, it is the phase which produces most energy per nucleon, about 6.6 MeV per nucleon, which is produced by hydrogen burning. And also it is a phase during which in a massive stars, the whole central region is turbulent, is boiling by what we call convection. And this boiling part in massive stars is more important. This boiling part is more important during hydrogen burning than in the later phase. And it makes the hydrogen burning phase the longest one. I have shown here, this is a bit more technical, but it's just to show a point. Actually, what you can do, you compute 25 solar mass stars, and what is shown here is the interior of a star. So again, it's 0 here, it's about 25, it would be over there, and here it's just the central part of the star, because the rest is boring, it's flat in these models. And what is represented here is you start from the surface, let us say 25, and you integrate the whole oxygen, which is between 25 and 24, between 25 and 23. So you integrate the oxygen going deeper and deeper inside the star. From all the exterior layers, you have a very small quantity. We have the quantity that you had at the beginning, which is small actually. In a star like the Sun, for instance, you have 70% is hydrogen, 27, I would say 28% more or less is helium, and 2% are heavy elements, and among these 2%, half is oxygen, 1%. So here you have 1% of the mass fraction that you integrate, and at a given point, you are, so at the ZAMS, you continue to integrate over the whole, you have the whole, ZAMS is the 0H main sequence. It's really the beginning of the hydrogen burning phase. So at the beginning of the hydrogen burning phase, the star is made from the same stuff in terms of chemical composition from the center to the surface. And so you just integrate the initial oxygen abundances over the whole stars. So you got a little bit here of oxygen. It is the oxygen that you could extract by destroying the stars at that stage. Now, if you do at the end of the helium burning phase, so it's the slope number 2. Then, when you arrive at 6 solar mass, you enter into the helium core, where a lot of oxygen is present. And when you integrate, you have this slope here, you see. So, if you would destroy completely the star, you would produce about more than 4 solar masses of oxygen. Now, you have to account for the fact that part of the mass of the star will be locked into the neutron star, which is taken as 2.5 solar masses. So this mass will not participate to the enrichment of the interstellar medium. It will remain locked into the neutron star, and only that part. And you will see that the 25 solar mass stars will contribute to about 2.8 solar masses of oxygen. Actually, if you look at the further numbers, 3, 4, 5, 6, 6 is the end of silicon burning. So you have some vibration of this curve, because you have some phase which destroy a little bit of oxygen, some others which will produce a little bit of oxygen. So you will have some effects of the advanced phase. But nevertheless, what I want to show you is that at the end of helium burning, you have already the correct answer, more or less, at a few details. So this is what we do when we are doing nucleosynthetic predictions. We are computing the evolution of a mass, and we are computing how much of a given element is produced by this mass and could be ejected at the time of the supernova explosion. We can do it for a population of stars, and this is a typical diagram that we did with our code in Geneva a relatively long time ago. It was but it's just to give you the idea. We have here the initial mass of the stars, and it goes, we are looking to massive stars. So it's between 9 solar masses, and the most massive stars is 120 solar mass stars. What is below the black line here is the mass, or the fraction mass of the star, of the initial mass of the star, which remain locked into the remnant, either a neutron star or a black hole. And here we suppose that even if we have black hole, we still eject something, which at that time was okay. Today it would be a little bit different. We have tendency to say that nothing will go out. So it will make that all this will be in the black hole. If we take, for instance, the 20 solar mass stars, you will have that this fraction of the mass remain locked. This fraction is expelled during the supernova explosion and is under the form of new elements like neon, magnesium, silicium. And this part, it's about this, I don't know, it's in fraction of mass, so you have to take the difference between these two quantities, multiply by 20 solar mass to have solar masses of oxygen which is ejected. And you have here in carbon and helium and so on. What is important, we have here stellar yields. It means that it's really the quantity of new oxygen produced. So it means that we have subtracted the oxygen which was originally present in that part of the star at the beginning of the history. So it's really the part which has been synthesized newly by the stars. And you can do this for all population of stars, and you can have yields for oxygen 12, for oxygen 16, for carbon 12, for nitrogen 14, even for isotopes. You can produce stellar yields. Now, as I want to come back to some principle of stellar physics. Actually, a star is at the same time something which is simple and something which is quite complicated. It's simple because, as I said, it's mainly driven by gravity, and most of the time it has mechanical equilibrium. There is a balance between gravity and pressure gradient. So it's a simple object. I must say that it is a place of the universe where you have the interaction between the 4 fundamental forces in the universe: the strong and weak nuclear forces, electromagnetics, and gravity. Actually, gravity and strong nuclear forces are important for the energy source of the stars. Weak forces and electromagnetic radiation are important for the transport of energy, for the radiation of a star. So the simple part is that they are at hydrostatic equilibrium. The complicated part is that there are many hydrodynamical phenomena in stars. You have convection. You can have also, when the star is rotating, meridional circulation, shear diffusion. You can have instabilities of the internal magnetic fields. You can have mass which is removed by stellar winds, for instance. So all these hydrodynamical phenomena makes that all the nice orders of magnitude that we obtained before are nice, they are correct more or less, but still sometimes they fail crudely for some points. And although stellar evolution is a well-established theory, there are many points where we are far too well understood what happens. And this is not just the details in the position of the nth decimal in the numbers. It's sometimes orders of magnitude of differences. And it can be the case for yields of some elements. So this is what makes stellar physics complicated, is how to deal with all these hydrodynamical phenomena. Now I want just to illustrate this by one hydrodynamical features. I could speak about convection, about instability induced by rotation. Actually, in Geneva, we did a lot of works in the past 2 decades on the impact of axial rotation on the evolution and the nucleosynthesis of stars. But I will not touch this question because it's a bit more complicated to explain. But I will simply touch one case, which is stellar winds. Actually, stellar winds are due to the fact that when we go toward more massive stars, the star becomes more luminous. I remember you, luminosity varies as m to the cube. So if you increase by a factor 10 the mass, you increase the luminosity by a factor 1,000. And as you may know, the radiation exert also a pressure on the matter. Actually, the first who found that point was Arthur Eddington. Arthur Eddington was very famous because he participated to the mission that observed the deflection of light of a star whose light was grazing the sun and which was deflected by the gravity of the sun. So he was one of the guys who proved observationally a prediction of the theory of general relativity. And Arthur Eddington wrote a book which is called Constitution of Stars, where he said that stars are sustained also by the radiation pressure. And he was also saying that if the radiation pressure would have, or if the matter would produce too much obstruction to radiation, the radiation would push the mass and would destroy the star. This is the principle of stellar winds. Actually, stellar winds were predicted well before they were observed. And they were observed thanks to spectroscopy, especially in ultraviolet by the EUE satellite. And stellar winds have a lot of impact on the way stars are evolving. I have no time to go into this list. As I said, this is due to the radiation pressure exerted by the radiation on the matter. We can see some effect on the spectroscopy, on the spectrum of a star, of stellar winds. And one of these features is what we call P-Cygni absorption profile. This is this kind of profile. You have a line which is due to one element, for instance to helium-2, carbon-4. It's generally a highly ionized species because it's seen in luminous and hot stars. And you have an emission here and an absorption. But it's due to the same element. How can it be the case? If you have a star which is surrounded by a strong wind, a strong wind can be seen as an expanding envelope. So the matter is flowing away from the star. When you are collecting the light coming from the side of the stars, so not the matter coming from the front of the hemisphere, but from the side. From the side of the star, you will have a matter which is hot, which will emit light. It will produce emission line, and this emission line will be coming from atoms which are, for one part, coming toward us, and from one part, going away from us. So the central wavelength will correspond to the emission in the rest frame of the star, and there will be some broadening to the fact that there is an expanding wind. This part is responsible for an emission line, while the matter, which is in front of the star, will be hot too, exactly as this one, but less hot than the star which is behind, and it will produce an absorption feature. But this absorption feature comes only from matter which is coming toward us. So it has only be blue shifted. So the blue shift will make an absorption which lower, I would say, wavelengths. And I would say the combination of the two make what we call the Pessigny profile. So the Pessigny profile is a sign of a strong, thick, expanding atmosphere of the star. Thanks to this, I don't know why, I think that I took these figures from a Chinese colleague, sorry for that, because it exists also in English and in French even, but I didn't notice that until now. Anyway, it's a way of quantifying the quantity of mass which is lost per unit time, here per year, for stars of different luminosity and colors or effective temperature. Here, what is the color of the star? We have very hot star here, very cool star here. And you have line of constant mass loss rate. What is important, you see, is to remember is that when you are more luminous, you lose more mass. And it actually sustains the idea that this is the passage of the radiation through matter which push the matter and produce the loss of the mass. So the strongly mass-losing stars are either the very luminous one, the massive stars, or also the evolved red stars, because here you produce dust and radiation has a strong impact on dust by pushing them out. We could say, okay, the wind for the massive stars are great, but we can say, yes, they are great, but the massive stars have a short lifetime. So it may be that even if they are great, it's too short to have an impact, you see? But it's not true. You can show this in the following way. I will just put like this. Actually, the mass loss rate depends on the luminosity. Depends on the luminosity about 1.7, at least in the hot regime. Now the luminosity in this mass domain depend on mass to the square, not mass to the cube. Actually, the cube is a kind of average mass-luminosity relation for most of the stars that up to 15 solar masses. But if we go toward higher masses, we have to account for the radiation pressure, and we didn't do that when we make this, when we obtain in the first lecture or the second lecture the mass-luminosity relation. We account just for perfect gas, but it's not correct for the most massive stars. For the most massive stars, they are also sustained by radiation pressure, and this tends to flatten the mass-luminosity relation. Since here we are speaking about massive stars, we have to use this relation between the mass and the luminosity. So you can see that the mass loss rate, if you put L proportional to m squared, will be proportional to m to the 3.4 power. Now the main sequence of the massive stars decreases with the mass. And it decreases by using this relation as m minus 0.6, more or less. This is by using stellar models. So when you increase the mass, you decrease the mass, you decrease the lifetime. So the quantity of the mass which is lost during the main sequence lifetime will be this time multiplied by this mass loss rate. And it will vary as m to the power 2.8. So actually, even if you have a shorter lifetime, the increase in mass loss rate largely compensates for this, and you will lose a large amount of mass. If you look at the delta m over m, you see it's more or less like m to the square. And actually, when we look at massive stars, especially some stars that we call the Wolf-Rayet stars, we can see that we have nearly evaporating stars. This is a famous picture of such a star, which is losing a lot of mass. Actually, these stars, at the beginning of its life, had about 60 times the mass of the Sun. So it's a massive star. And it is believed that at the end of its lifetime, and this is of course due to stellar models, it's not something that we can observe, at least we can, for some of these stars, determine the mass, and it's compatible with these numbers. And at the end of the life, they have only 14 solar masses. It means that they have lost during their lifetime, before the supernova event, due to stellar winds, about 46 solar masses. 46 solar masses. By the way, we can even speak for these stars about mechanical stars, in the sense that the energy that they release under mechanical kinetic energy is no longer negligible. Actually, you can compute the mechanical energy of these stars like the kinetic energy of the mass loss rate, 1/2 the quantity of mass lost per unit time, multiplied by the velocity of the wind to the square. And for the hot star, the velocity is a few thousand kilometers per second. And so you can show that the mechanical luminosity is about 30,000 the solar luminosity. But of course, the luminosity, the actual luminosity of these stars is higher than 30,000 solar luminosity. And so the ratio between, this is the contrary, sorry, I made a mistake. The mechanical luminosity divided by the total luminosity is about 10%. What is interesting, if you integrate over a lifetime of the phase during which that star has a strong wind, which is about 500,000 years, you obtain that the mechanical energy which is injected into the interstellar medium is about 10 to the 51 ergs. And 10 to the 51 ergs, you know that in May I will go to a conference which we call the 51 ergs conference. Actually, it's a conference dedicated to supernova explosion. During a supernova explosion, the typical average mechanical energy which is injected into the interstellar medium is 10 to the 51 ergs. Here you have the same amount, but of course, instead of doing it in a very short time, the time of a supernova explosion, you need 500,000 years. Okay. Now, this mass loss has an extremely nice feature. It is a bit like nature helps us in order to understand stars. What I mean here? Actually, what is shown here is the evolution of the total mass of a star. You have the evolution of the total mass as a function of time, which is expressed in million years, and the total mass is decreasing with time, you see, because of this mass loss. And at a given point, we enter into a phase of very strong mass loss, and which makes the decrease to be very rapid in a relatively short amount of time. The red part here, the first red part here corresponds to the hydrogen burning core. It is, all this region is turbulent, and it means that at every moment you have the same composition, and the hydrogen mass fraction is decreasing as a function of time. At a given point, hydrogen has been completely, I would say, used to make helium, and you have apparition of a new nuclear burning phase, which is the helium burning phase here. And here you have the convective helium burning phase. What is interesting here, you see, when due to mass loss, you see that layer. That layer in the past was just here. So it was just beginning to be transformed by nuclear reaction due to the core. And so at that point, you will see some change in the chemical composition. When you continue, at a given point, you will see very strong decrease of hydrogen due to the fact that hydrogen is transformed to helium. And even here, you can see the beginning of helium burning products. So you see by removing its outer layers, you can look inside the star to make a kind of tomography of the chemical composition of the star. Of course, you will have here you will see some composition which results from the whole phase during all that phase. But you will see some change in this chemical composition because at that point you have already some change of the chemical composition due to convection. And this will increase when you remove mass of the star. This is a plot showing how the surface composition of the star is changing when you remove mass. So what is indicated is not the time here, it's the decreasing mass. You start from a 60 solar mass stars, you remove 10 solar masses, you remove again 10 solar mass, 10 solar mass, and so on. And you can see how the chemical composition change. You can see that at the beginning you see the initial composition of the star, which is hydrogen, helium, you have oxygen. Then you begin by seeing the product of hydrogen burning, so a lot of nitrogen, less oxygen and carbon because they are destroyed by the cyano cycle, helium, which is increasing because it's product. At a given time, we will see only hydrogen products without any hydrogen because hydrogen is completely destroyed into helium. And at a given point, you can see the helium burning products. And typically, I must say that in stellar evolution, in many cases, we are explaining what we have already observed. Here it is a case where there was a prediction. A prediction was that in some stars, which are called WC stars, I will not enter into the detail, if the nucleosynthesis is right, you should observe a lot of neon-22. So we can ask to our colleagues who are doing spectroscopy to see, are these stars rich in neon? Actually, it was not possible to ask neon-22, it's too much, because it's difficult to make here, I think, from spectroscopy, the distinction between neon-20 and neon-22. So here there is an assumption that what they will, it will be already nice to see whether they detect neon, whether it's neon-20 or neon-20, we don't know. But actually they did the work and they obtained an abundance of neon, which is in the right order, which is in the right value with respect to the prediction of the models. So this kind of, I would say, losing mass stars allow to check the nucleosynthesis in some way, or to check the nuclear reaction rate, or to check the nuclear paths. This is a bit complicated, but I will be very short. It means that, you know, the stellar winds is due to the obstruction of light when it goes through the matters. But this obstruction depends on the chemical composition. Typically, if I was God, which I am not, and if you take a star and you put more heavy element at the surface, you will make the surface more opaque. And you will increase the mass loss rate, you see? Because the radiation has more difficulty to go out, it will push more mass. Because this push is due to the fact that photons are absorbed and then re-emit in different directions. But there is a net force toward the exterior, which is due to this interaction of electromagnetic radiation with the matter. And these interactions become more numerous if there are more metals. So the winds are believed to be stronger in more rich or more metal-rich environment. And this is the point here. And it has interesting consequences for some population, but this I skip because it's a bit away of my talk. Now the point is the following one. We know that the massive stars have two ways of losing mass. One way is at the end of the evolution, when they explode as a supernovae, and the other way is through the stellar winds. If anyway, for at least a 20 solar mass star, the mass above the remnant is lost, is it very important that it is lost by mass loss, by stellar winds, or by supernova? Has it an impact on the chemical composition of the matter which is ejected? And the answer is yes, it has an impact. Why? Because you are ejecting mass at different stages of the lifetime of a star. When you eject at a supernova, all the layers of a star have been processed during a longer time. And typically you have some layers which were rich in oxygen, which could be transformed, for instance, or which were rich in carbon, typically, which can be transformed into oxygen, because carbon is transformed into oxygen. While the stellar winds occurs during the whole lifetime of a star. So it can remove some layers from a star and stop, of course, the nuclear reaction, because if you remove layers from the stars, you change the temperature, density of the layers, and stop the nuclear reaction. So you freeze at that given time, you see, the composition, and there will be no longer process. And so this is particularly important for oxygen. It's why I am showing you this here. Maybe just... Actually, you can take different stellar models. And whatever it is, the answer will be more or less the same, even with the most recent one. You can take models with a very low metallicity. Z here is a mass fraction of heavy elements. It means that typically in those stars, there was only 1/1000th of the mass which were in the forms of elements heavier than helium, typically cyano elements. And you have here a more metallic one, you have here with rotation, and so on. So you have different stellar models. What is represented here, now you compute all stellar population for this different metallicity. And you compute how much of new heavy elements in solar masses is ejected, whatever by the winds, whatever by the supernova, at the end of the evolution. So when suppose a population of massive stars with a total mass of, for instance, 10,000 solar masses, so you form 10,000 solar masses of stars, and you distribute them into 120, 40, all the domain of mass. And actually, what the numbers here mean that 4%, and if there was 10,000 solar mass, it means 400 solar masses of that matter will be ejected back and will be new elements. You see? So actually, it's not a very efficient process. You need 10,000 solar masses to make a production of 400 solar masses of new elements. And you can see that this 400, it varies a little bit depending on the physics, but it's more or less constant. It does not so much vary a lot. At least, of course, here we do more or less the same hypothesis for what happens, what remains locked into the remnant and what is ejected at the supernova event. But for the total numbers of heavy elements, it is not so much sensitive. Now, as I said, when you look at the contribution of the supernova event and the wind, you have differences. Typically, if I look at this case, which is a very high metallicity, you have 4%. Here you have 40 times more heavy element than here. You can see that here you have nearly no mass which is lost by the winds, because the blue part is the matter of new element ejected by winds. So at low metallicity you have nearly everything is ejected by the supernovae. While here you have more or less half and half. So now, is the chemical composition different? Actually, as I said, it will be different. I took here as an example the case of a helium core. Let us suppose that you have a star which has lost its hydrogen-rich envelope. So you have at the beginning of the helium burning phase a pure helium core with, and you have already some carbon-12 which has been produced by the beginning of the helium triple alpha reactions. If you have no mass loss in nearly all that mass of the star, if you suppose that you will have a lot of oxygen. Actually, not all will be oxygen because not all the mass will be transformed. But you will have something which is a fraction of this mass, but not so much less. And you will have at the end of the evolution a lot of oxygen because all that matter will be processed by the star. If you have stellar winds, you will eject helium and carbon, which will not be further transformed into oxygen. So at the end, you will have an ejection of carbon and helium, and the supernova will eject less of oxygen. So it's an example on how the winds and the supernova remnant change the chemical composition. So this is written here. And if I do now the same plot as before, let us look at the oxygen here. You see? So if we compare now the quantity of oxygen, you can see that in the low metallicity, a lot of oxygen is produced. About 1.6%, it will be 160 solar masses from the 10,000 solar masses that we spoke about before. Now, if I look at the regime where you have a strong mass loss, you have actually much less oxygen which is produced because of the effect I was just mentioning, because most of it will be removed by winds and the matter will be in the form of helium and carbon. So this just shows things that the stellar winds can save some elements from further destruction. Typically the carbon-12 and the helium can be saved from further destruction by being extracted from the star by the stellar winds. And this changes the yields. Actually, this kind of process can change a lot the yields of some elements like helium-4, like carbon-12, this is example, but also like fluorine-19, neon-22, the weak S-process component. And if I have time, I will say a few words about helium-26. Another point, very rapidly, is that of course the mass limit that produces black hole is very important in this process, because if we say that when a black hole is formed, everything is followed by the black hole, it means that the whole part of the mass domain will not contribute to the enrichment in new elements. So this is a point that has to be accounted for. Two last slides for these lectures. There are many more than the mass loss. There is the convection, there is some nuclear reaction rates which are not so well known, like the carbon-12 alpha-gamma O16 reactions, rotation magnetic fields, and especially now, not now, but it's a long time that is known, but it's particularly well studied now, it's binary evolution. The fact that when a star has a close companion, some mass can be transferred from one to the other, changing completely their evolution. In addition, once you have computed all this complexity of the stellar physics, you are not at the end of the story. You have to feed with the stellar yields a more complex picture of the whole evolution of the galaxies, with star formation, with the way then the stars which are formed, we inject into the interstellar medium the new element that they've built, new element that they can be used to form new stars, and so on and so on. So it's a complex picture, and stellar nucleosynthesis is just one aspect of it. But lithium is complicated because it can be built, destroyed by all the different possible sources of nucleosynthesis in the universe. It is built at the Big Bang, it is built in spallation reaction, it is built and destroyed in stars. You may know that today there is a big crisis about lithium because we can predict the quantity of lithium that was predicted by the Big Bang nucleosynthesis. And it appears that this quantity is 4 times above the lithium that we can measure at the surface of the oldest stars in the universe, which are probably reflecting the Big Bang nucleosynthesis. And this discrepancy of a factor of 3-4 has not been resolved yet. Some people have said it's because lithium that has been incorporated into these low mass stars has been destroyed by the stars themselves. But it forms a kind of plateau over a long metallicity range, except at the very low metallicity, I would say, where it's decreasing. And it is what we call the Spit plateau from Monique and the Spit and Spit, but I don't remember the name of his husband, her husband, which the fact that it is a plateau, it is as if it was the abundance everywhere in the universe. And if it is destroyed by the star, why it is a plateau? How the star know that they have to stop to destroy lithium at a given point? So this is a problem of lithium. Okay. Actually, maybe I want not to enter too much into star formation, but you have to, you see, if you take a molecular cloud is very often very massive, more massive than a star. Typically, you have molecular cloud with 10,000, 100,000 solar masses. But this is the contraction of such a molecular cloud that will produce stars. But it will produce not only one star, it will produce population of stars. I have no time to enter into this equation, but it's also very nice. But you know, that's just a point of physics. When the cloud contracts, it heats the gas, as I said. And if you continue to heat the gas, you will install a pressure that will stop the contraction. In order for the contraction to proceed up to stellar density, you need to evacuate this energy. So it's why the cooling processes in star formation are the key. You need to evacuate energy coming from contraction. Otherwise, you stop the contraction. And this is the main point that I wanted to say here. Just to show you a few images of beautiful star-forming regions. There is the Carena regions, and if you look in the upper part, you have the jets which are coming from young stars. This is invisible, this is infrared. So infrared you can see inside the cloud, because infrared is not obstructed by interstellar material, or less obstructed by interstellar material. So you have here very strong hydrodynamical phenomena like jets, for instance, and you have near the star some disk which is due to the conservation of angular momentum. And this is in this disk that we believe today that planets are formed. Actually, it's nice because from the little analytical, I would say, formula that I have shown very rapidly, you can obtain an interesting numbers. You see, you start from a molecular cloud, and you suppose that you can release the energy produced by the contraction, and this will produce fragmentation, because smaller part of the cloud will become unstable against collapse. And you can ask, what is the smallest fragments that you can form by contraction and fragmentation of a molecular cloud? And this was a paper by Martin Rees and another that I have forgotten the name now. And this smallest fragments is about 1/100th of a solar mass, 0.01 solar masses. It's interesting because it's less massive than the 0.08 solar masses. That is the minimum mass for stars. So the fragmentation process of molecular cloud can produce brown dwarfs, for instance. But the 0.01 is 10 times larger than Jupiter mass. So Jupiter, for instance, cannot be formed by this process, and probably is formed through accretion or through some other process instabilities in the protoplanetary disk. You have here some nice images in Orion, which is a star-forming region, of some what we call proplyds. And the disk lifetime, but I think that we will heard much more about this, is around 10 million years, if I am not wrong. And you have many of different processes occurring. But this will be more the topic, I guess, of the next lecture this afternoon. Nevertheless, okay. The point I would like is that by looking at meteorite, by looking at the chemical composition of a few milligrams of a meteorite, you can try to reconstruct at least part of the history of the whole solar system. And this is, for me, amazing also. Actually, the point is that, but this, I am working in a field where I am less confident. But what I have heard from Mathieu Gounel and others is that you have some strong evidence that some short-lived radionuclides have been injected inside the protoplanetary nebula. You take an element like aluminium-26. Aluminium-26 has, I would say, a mean lifetime, the time for the fraction E, E being the natural logarithm, or the lifetime for the quantity of aluminium-26 to decrease by a factor E is about 1 million years. Or the half-lifetime will be 700,000 years. So it means that if I have 1 kilo of aluminium-26, I go on holidays, 750,000 years after I come back, I will have only 500 grams, half a kilo of aluminium-26, which remains, and the rest will be transformed into magnesium-26. Now, what I find puzzling is that we can have some evidence, that in some meteorite, there was at a given time, inside the meteorite, some live aluminium-26. I mean, some aluminium-26 that has not decayed, that has decayed inside the meteorite, you see. And for me, it's strange because, of course, if you say that aluminium-26 has decayed in 1 million years, you look at a meteorite 4.5 billion years after, how you can recognize the magnesium-26, which was at the beginning in the meteorite, from the magnesium-26, which result from the decay of aluminium-26. And actually, you can do this by making a plot. And in the horizontal axis, you will put the ratio of two elements. You will put aluminium-27 divided by magnesium-24. And on the vertical axis, you will put magnesium-26 divided by magnesium-24. And you will measure these two ratios in different meteorites. Actually, when you have two different elements, like aluminium-27 and magnesium-26, you do not expect to have a constant value in every meteorite because you have different chemical properties. And they will be cooked differently in different meteorites. And so the ratio will change. So you will have a large range of aluminium-27 over magnesium-24 ratio. For the vertical axis, it's different because you have the same isotopes. So if everything was more or less, you would expect that the same isotope, magnesium-26 and magnesium-24, will react to the same history. And the one which are in a given meteorite has the same history in some way. So it keeps this ratio. Actually, the fractionation, the physical processes will keep more or less this ratio constant. So what you expect is that if you measure 26 over 24 with respect to 27 over 24, you expect to have a kind of horizontal line. But actually, what is observed is different. You have a line with a slope. And actually, the vertical axis, magnesium-26 over magnesium-24, can be decomposed. You can say that the magnesium-26 can be decomposed in two parts. The magnesium-26, which was already present in the meteorite at the moment of formation, which I have called magnesium-26 zero, and the magnesium-26 coming from the decay of aluminium-26. And this is equal to, I can divide by the quantity of aluminium-26, of aluminium-27, sorry. I can divide and multiply, so I will not change the first term, and the second term I don't change it. What is interesting is that you have a kind, you see, of linear relation. You have the ordinate at the origin, which will be magnesium-26 0 divided by magnesium-24, and you will have a slope which will be the magnesium-26, which come from the decay of aluminium-26, divided by aluminium-27, which will be the slope of this line here. Because here you have aluminium-27 divided by magnesium-24. So your slope gives you access, if the interpretation is correct, to the quantity of aluminium-26 which was present in terms of aluminium-26 at the beginning of the formation of the meteorite. So the question, so it tells you something. It tells you that when this meteorite formed, there was a ratio of radioactive aluminium to stable aluminium. This ratio was about 5.1, 10 minus 5. So this is interesting information. I think that you will feel very much happy in the rest of the day by knowing that, I guess. But anyway, it's interesting because you can have different, first of all, there are different of these short-lived radionuclei. There is not only aluminium-26, there is also iron-60, and there is other one. But I will focus on aluminium-26. The point is, where does this ratio come from? It can come from the fact that it is a normal composition of a molecular cloud. And everywhere where you have a molecular cloud in the galaxy, more or less, you will more or less expect to have this ratio. Or you can say, no, it has been injected by a source in the vicinity of the solar system. And this would make the solar system a little bit special because it needs this source, and you can have formation of planet in which this source is absent. So it's an interesting question, you know. It's an interesting question to know where does these short radioactive elements come from. So as I said, it can from ejection of this aluminium-26 from a special source. It can be an IGB, like Giuseppe has studied. It can be the wind of a massive star, a supernova. It can also come from the normal aluminium-26 abundance in the galaxy. But do we know the normal aluminium-26 abundance in the galaxy? We have some hints, actually, because we have observed the gamma ray line coming from the decay of aluminium-26, thanks to gamma ray satellite. The first one we have observed it was the High Energy Astronomical Observatory 3, HEAO 3, a long time ago. Then there was Compton. Today there is integral, and you can make a map. You can make a map which is obtained by collecting the light from the decay of aluminum-26. It's at a given energy, which is 1.8 MeV. And one of this map is the following one. And we have a diffuse emission. We have not point source, like the light of the stars and so on. We have a diffuse emission because aluminum-26 is produced by stars and injected into the interstellar medium by supernovae, by AGB, by Wolf-Rayet stars, by wind stars, and then it will mix and it produces a diffuse emission. What is interesting, of course, you need some models here, but you can obtain the quantity of aluminum-26 that there is in the whole galaxies. And it's around 1.5, 1.8, 2 solar masses, let us say. There are some, of course, because you don't know exactly the distance, but you can make some reasonable, I would say, assumption, and you obtain it's around 2 solar masses of aluminum-26 in the present-day galaxies. By the way, it's also a proof that you have some metabolism, because in order to have 2 solar masses of aluminum-26 in the galaxy, if this aluminum-26 was simply the decay of a huge amount of aluminum-26 that was born in the Big Bang, for instance, you have 30.8 million times to decay, so you have to start with an incredibly enormous amount. It's not possible. So it means that this aluminum-26 has been produced by stars in the galaxies. So it's a kind of proof of stellar nucleosynthesis in some way. An observational proof that indeed matter is transformed by the evolution of stars. Now, if you take this quantity and you divide by the mass of interstellar material and you compare with the ratio that we observe in the meteorite, you will see that in the interstellar medium, the quantity which is deduced from this total quantity divided by the total mass is lower than the one that we observe in the solar system. This is the plot here. But there are some people like Edward Young, for instance, who says, but be careful, there is no star formation everywhere in the interstellar medium. It's only in the molecular cloud. And if you take the mass of the molecular cloud, and you say that all the aluminum-26 is inside this molecular cloud, then you get something normal. You get normal in the sense that you get the aluminum-26 over aluminum-27 ratio, which is the one that you observe in the solar system. So in which case, every molecular cloud would have the ratio, which is observed in the solar system, and nothing will be special. The problem is that there is iron-60, and it will not work with iron-60. So I think for me, but again, I am open to discussion, it seems that aluminum-26 has been injected by a source at the beginning of the solar system. And the question is, what was the nature of this source? I will stop here.